Oh, half angle!
Double angle, half angle,
Power reducing formulas / identities.
I don't know if we'll get through all three of them today.
That's a lot. I was gonna say normally like
The next thing to take a look at is just more identities. Double angle, half angle, and then also power reducing. Right? I do not have the quizzes all graded yet. It might take me a little bit because I go through the entire process for your proofs for the identities instead of just looking for an answer. Right? So hopefully I can get those back to you in a day or two. So I intentionally did not. There's a lot of research saying that writing stuff down helps you remember it.
that's right.
Me?
I
swear. Yesterday, before I came into school, I didn't know any of those things. And I memorized them all like that.
You didn't have
Dude, I'm good at this stuff.
well, you already hurt my feelings.
I'll write it down. Because
I know.
don't want you to
Well, if I'm not giving it, so
Stick that right in your eye.
look at them and memorize them. Okay, so we have just one double angle formula for tangent. Okay, and these are all just different forms of Pythagorean identities on the right side. So if you, and again, we talked about ways to derive the different Pythagorean identities if we just know that sine squared plus cos 1. Similarly, if we just know this first one, we can fairly easily derive these other two, just knowing that Pythagorean equals 1. So I could subtract either of these identities over, or either of these pieces over to the right side, or I would have cosine squared equals 1 minus sine squared. So I could substitute 1 minus sine squared in place of cosine squared and make this cosine of 2x 1 minus sine squared of x minus sine squared of x. So that's how we get this second form of the Pythagorean identity, or of the double angle identity for cosine. We've got 1 minus sine squared, so that would just be minus 2 sine squared. Similarly, to get this one down, I could take my original Pythagorean identity and subtract cosine squared over. Make this 1 minus cosine squared, and then substitute this in place of sine squared. So we could make this cosine of 2x equals cosine squared of x minus 1 minus cosine squared of x. So we end up with cosine squared minus negative cosine squared. So that would be cosine squared plus cosine squared. So that's where we get the 2 cosine squared, and then negative 1, so minus 1. So both of these forms of the double angle formula for cosine are again just manipulations of this original one using Pythagorean identities. Okay. Got all these copied down?
You want us to copy down the two you just put on the board?
Well, these are just how we get these two. So if you want to write down those steps, I mean, it's totally up to you whether you just want to memorize all 3 of these or whether you just want to memorize this first one and then understand how to derive these two from this one. Just like for the Pythagorean identities, right? It's up to you whether you just wanted to memorize this one and then understand that we could divide everything by sine squared to get one of the other ones, divide everything by cosine squared to get another one.
So we're gonna have to memorize.
Oops, I didn't want to have that up there.
We're gonna have to memorize those, and then also the half angle stuff, and then the other third one for the test.
You don't need to know the power reducing ones for the test. I will give those to you.
That's still what is that, like 67% bad? 2/3? I'm smart.
I'll give you a list of what you need to have memorized and what you don't need to have memorized. Alright, so the double angle formulas are used to find exact values of double an angle that we know. Now, for the previous section where we used the sum and difference formulas, those allowed us to find things like cosine of 15 degrees or sine of 75 degrees, angles that we didn't already have exact values for. If we take any angle on the unit circle and double it, that's just going to give us another angle that we already know the exact measurement of. Okay? So problems like this are how these formulas are going to be used. So in this example, we've got cosine of theta is -3/5, and theta is in the second quadrant. So we can sketch out our picture. Our angle here, the second quadrant. And I know cosine, which is adjacent over hypotenuse, is -3/5. So I want to find the exact value of each of these expressions. So first, we would want to find this missing side, because for each of these formulas, we're going to need sine and cosine. So if you recognize it right off the bat, this would end up being a 3, 4, 5 right triangle. So our missing side here would be 4. And it would be +4 because the y value is positive here. If you don't recognize that it's a 3, 4, 5 right triangle, you can always use the Pythagorean theorem to find that missing side. So we could have done -3² plus b² equals 5². Solving that, we would get 4. Okay. So now, if I want the sine of 2 theta, well, they already have it. Oh no, they don't have it written out actually. So sine of 2 theta, we're just going to go back and use the formula from the previous slide. Right? So sine of 2 theta, or sine of 2x, is just 2 times sine of theta times cosine of theta. So we can get each of those values from our triangle. So sine of theta is just opposite over hypotenuse. So that's 4/5. And then cosine of theta is adjacent over hypotenuse. So -3/5. So just do the arithmetic now. So 2 times 4 times -3 would be -24 over 5 times 5. -24 over 25. Do the same thing for each of these then. For tangent of 2 theta, that's 2 times the tangent of theta over 1 minus the tangent squared of theta. So again, we can get tangent of theta from our triangle. So tangent would be 4 over -3. So 2 times -4/3 over 1 minus -4/3 squared. And we do want to simplify this then. So 2 times -4/3 would be -8/3 over 1 minus, so -4/3 squared. I would square numerator and denominator, and that would be 16/9. That value would then be positive, because squaring a negative value gets me a positive value. So then we want to simplify the denominator. That's subtraction. So 1 minus 16/9, we want to get common denominator, so we can say this would be 9/9 minus 16 over 9. That would end up being negative 7/9. And then finally, to simplify a fraction over a fraction, that's the same as multiplying by the denominator. Right, so we've got negative 8/3, and we'd be multiplying that by negative 9/7. So before we multiply, we can always cancel out factors. So this 9 and the 3, I could reduce that to 3 and 1, and multiply straight across. So negative 8 times negative 3 would be 24 over 1 times 7 would be 7. Then finally, cosine. Right? It really doesn't matter which formula we choose. We know both sine and cosine, so it doesn't matter. I'll use the first one. So for this example, cosine of 2 theta will be, and I'll just go ahead and square. So cosine of theta is negative 3 over 5. So negative 3 over 5 squared minus sine be 4 over 5. So minus 4 over 5 squared. Square those values. So negative 3/5 squared would be positive 9/25 minus 16/25. So that would end up being negative 7/25. So we've done problems like this before where we had to use a right triangle to figure out different measures, and now we're just using these formulas to find double angles. Okay. Questions on something like this? Do we want to try another one like that, or do we think we're good? Good? All right, cool. Then we're going to skip the power reducing identities. We'll come back to those. Let's do the half angle identities
There's
first.
a memorize all these too.
I believe so.
So we have to know all of these.
The double and half angle, yes, but not the power reducing ones that we'll look at.
And one to memorize all the ones.
Yeah. Right. Yeah. So let's take a minute or two to jot these down.
Mr. Fetch,
So
your last identity slide was using x as a variable, now it's theta. I don't really like your inconsistency.
that's intentional because you can use x, theta, alpha, use a star, whatever you want.
I think you're justifying something that's obviously incorrect.
Yep.
So is the velocity dependent on if it's 1 or 2 or 4? So 1 and 2 is positive.
For sine, yes. Cosine would be 1 and 4 are positive, 2 and 3 are negative. Cosine is the x value. And the tangent is 1 and 3 are positive, 2 and 4 are negative.
I do think theta over 2 looks a lot cleaner than x over 2. Sounds like you're just complaining to me.
So in addition to the formulas, make sure that you write down this sentence underneath as well. Okay, this is important to determine whether our value should be positive or negative. So if our angle in question lies for sine, sine is the y value, right? So if we're thinking about quadrants 1 and 2. Quadrants 1 and 2 are positive y values. Alright, so in quadrants 1 and 2, this will be positive. If our angle is in quadrants 3 or 4, this value would be negative. For cosine, cosine is the x value. So we're thinking, well, x value is positive in quadrants 1 and 4. And then the x value is negative in quadrants 2 and 3. Then for tangents, since tangent is sine over cosine, we've talked about quadrants 1 and 3 would be positive for tangents, and quadrants 2 and 4 would be negative.
We're gonna have to memorize all of that.
Well, I mean, hopefully we kind of see that, because what we're saying is, we know that sine is the y value. So the y value, if we're looking at coordinate plane, the y value is positive if we're up here. So that's quadrants 1 and 2. It's negative if we're down here. Same idea for cosine, right? Cosine is the x value, so that would be, these two would be positive, these two would be negative. Questions so far? Alright, so this, I thought that I did not put that solution on there. Let me change that real quick. So this does allow us to find exact trigonometric values of other angles. So so we can use a half angle formula to find the exact value of cosine of 157.5 degrees. So what we're thinking to use our half angle formulas, we're thinking that cosine of 157.5 is the same as what over 2. Right? That's how we're going to use our half angle. So to figure that out, we would just double this angle. So if I double 157.5, I believe that gets me 315. Okay, so this is going to be the same as cosine of 315 divided by 2. Well, if we go back and look at our formula for the cosine of theta over 2, we're just going to say this is equal to the square root of 1 plus the cosine of theta. So theta now is 315. So 1 plus the cosine of 315 degrees over 2. Now, to figure out whether this should be positive or negative, we think about our original angle. So this 157.5. What quadrant would 157.5 degrees be in? 2. It'll be in the second quadrant. Right? So is cosine positive or negative in the second quadrant?
Negative.
Negative. So that means that our value here should be negative. Right? So now let's just simplify. So what is the cosine of 315 degrees? You can look at your unit circle. You do not have to have the unit circle memorized. So if we look at the unit circle, what is the cosine of 315?
Do you remember when at one point you thought we might have to have it memorized? How could you ever?
Well, a few years ago when I taught pre-calc, I made kids memorize it.
You're
I had to memorize
you're
it.
evil.
Yeah. Remember we had to memorize it.
I should call you Joseph Stalin. More like Fach Stalin. No, the left. You have to arrange completely.
So what is the cosine of 315?
I'm weird.
Square root of 2 over 2. So we have figured 1 plus the square root of 2 over 2 all over 2. Right. We want to simplify this a little bit. So we can start a few different places, but we could start by combining our terms in the numerator. So to do that, I would need to get common denominators, so we can make this 2 over 2 plus the square root of 2 over 2, all over 2. So we end up then with 2 plus the square root of 2 over 2, all over 2. Well, dividing is the same as multiplying by the reciprocal. So dividing by 2 is the same as multiplying by 1/2. So I could really make this 2 plus the square root of 2 over 2 times 1/2, like that. Okay, dividing by 2 is the same as multiplying by 1/2. So then this would become 2 plus the square root of 2 over 4. Now, to simplify, we're not allowed to have radicals in the denominator, right? So technically, we still have a radical in the denominator here, right? Because if I'm taking the radical of a division problem, I can split that up, right? I could make this the square root of 2 plus the square root of 2 over the square root of 4. And remember, if we're taking the square root of a fraction, we can take the square root of the numerator and denominator separately. But now, square root of 4, that's a perfect square. Well, that's depressing. So, the square root of 4 is just 2. And technically, this is a simplified answer. We are allowed to have a radical inside of a radical. Right? Yeah. As long as we don't have a radical in the denominator. Not always, but sometimes, yes. Okay, so negative because 157.5 degrees is in the second quadrant, and then square root of 2 plus square root of 2 all over 2 is the exact value of cosine of 157.5 degrees. Questions? Do we want to try another one? How about we do sine of 22.5 degrees. Find the exact value of sine of 22.5 degrees.
You tricky dog.
The value should be positive because 22.5 degrees is in the first quadrant. Right. Questions on something like this? Do we want to do another one? I think we're okay. All right, then I think we will save the power reducing formulas for tomorrow. That's not the right homework. So let me put a couple of problems up here for us to try.
Mr. Fetch.
My book. Anybody have a book?
No, Brady will. Brady's got his book, guaranteed.
I'll go get my book.
Look at that. They can never go get his book.
Take it out of your bag.
How incredible disrespect.
What was it? You're saying that you want me to kill you? Are you sure? Damn, you should reconsider. I don't appreciate it. I think you'd appreciate it. Mr. Fetch, want a spring break?
March 20th is our last day. Next week.
And then we graduate?
No, not then we graduate.
Oh man, can't wait to either way. Mr. Fetch, do you think Mr. Milano is like the ultimate example of someone who peaked in high school because he maximized his career and the education of this kid, specifically in high school?
You could say it that way.
All right. Here's our homework for tonight.